We've seen already that the aldehyde condensation can give us an alpha-beta unsaturated aldehyde. When that forms, or in the process of that, we can see this here is in resonance. These electrons can form a double bond. That goes up there. So that is one resonance contributor. And there is another one. There's a positive charge here. And there's another one I can move with these electrons there. This is still negative. My positive is now here, and the double bond is there. So these are all in resonance with each other. So there's two different electrophilic portions, one on this carbon here and one on the carbonyl carbon. So if you are doing a Grignard attack on an alpha-beta unsaturated carbonyl, the carbon bond will be formed at the 1,2 position. So this is 1, 2. The Grignard is going to attack here. That double bond stays where it is. This O becomes an alcohol. So we have addition of R, and then we get protonated. If you use a Gilman reagent, that is going to attack the 4 position. So 1, 2, 3, 4, and do a 1,4 addition or a conjugate addition. So it's adding to the conjugated position there. We only add one, R group. And you lose the double bond in the process. And we'll see why here. So the nucleophile, this is the Gilman, is going to attack at the 4 position. This is gone here. I have a new bond to the nucleophile. This is O-, and then there's acid present. Get a proton transfer. This is the enolate. This is the enol. Did a tautomerization. So there's a proton shuffle, double bond, and there's an H that appears here. So more reactive nucleophiles like the Grignard are more likely to attack the carbonyl directly. The enolates are generally less reactive than Grignards, but more reactive than Gilman reagents. So enolates can give a mixture of 1, 2, and 1, 4 additions. If you have doubly stabilized enolates, these are stable enough to react primarily at the beta position. So this is one that is doubly stabilized because it has resonance between the 2 carbonyls here. So if I did a reaction here, the KOH is going to form the enolate at this position. The enolates here are going to attack at the 1, 4 if it's doubly stabilized, so that's going to attack here. Throw a new bond, that's the 4, this is this bond. So that's what you would get there. So the conjugate addition at the 1, 4 position. This is 1, 1, 2, 3, 4, 1, 2, 3, 4. When an enolate attacks a beta carbon, or the 1, 4, the process is called a Michael addition. So we have Michael donors. These are all the ones that are doubly stabilized. And these are Michael acceptors. So this is where it's going to attack at the 1, 4 position. So if you use the combination of these with these alpha-beta unsaturated carbonyls, or you have nitro and nitriles, you'll get a 1, 4 attack. Singly stabilized enolates do not give high-yielding Michael additions, and Gilbert Stork developed a synthesis using enamine intermediate, and Gilbert Stork would be the equivalent of my, I think, great-grandfather in PhD family tree. My boss's boss worked for Gilbert Stork. So that's my PhD lineage there. So Gilbert Stork is in my family tree for PhDs. He used an enamine intermediate where you react a carbonyl with a secondary amine, which we've seen to make the enamine. We get this enamine. So their enolate can form normally. This would be an enolate where this is a minus charge. If you were attacking a conjugated system, it could attack at 1,4 or 1,2. The enamine is going to attack at 1,4 only. So we take this and add a Michael acceptor to it. This is partially positive. This enolate can attack here. So you end up with O minus there. And then on the next slide here, we add acid to that. And we know that acid will reverse this and turn it back into the carbonyl, and that will tautomerize the enolate. And we get the secondary amine back. The Robinson annulation utilizes a Michael addition followed by an aldol condensation. So after Michael addition, which is the enolate forming here, and that will attack there. We form a new bond. 1, 2. So that gets added. And then we add NaOH and heat to do the aldol condensation. So in the aldol, this is the enolate here. Enolate, and that's going to attack at this carbon. So if you remember when we did the aldols, we're going to form a bond to the new carbon and to this position here. So lop off that oxygen and then stick that double bond there. So this is my new bond. I have this carbon. This is my carbonyl carbon. That's my carbonyl carbon. This is the enolate carbon. And this is the double bond that formed. So you get a nice ring. So a Michael addition followed by an aldol condensation is the Robinson annulation. So you form cyclohexenone. All right, so we're going to power through a mechanism here. Sodium hydroxide is going to pull off this proton, which is doubly stabilized. pKa of that one is around 9. So then I form an enolate. All right, so the first is the Michael addition. New bond, 1, 2. Call this a proton transfer, even though it's a tautomerization. More NaOH. Going to grab this proton. And then that can now attack here. New bond, and I have an O minus. All Alright, get a proton transfer. There's an acidic proton there. And then we get that product there. Okay, so to identify reagents that can be used to prepare the following via a Robinson annulation, there are a couple of tricks here. So you first want to label alpha, beta, and gamma on your ring, starting from the alpha position. So find the ketone in the product, which is here, and number the saturated side, alpha, beta, gamma. Divide the compound in half between the double bond and the beta gamma bond. So double bond and the beta gamma bond. The half with the C double bond O was the alpha beta unsaturated ketone, and the double bond was between alpha and beta. The ketone is the other half. So you can think about prying those pieces apart. Okay, so the half with the carbonyl was a alpha beta unsaturated ketone. This part has the carbonyl. So that's the CH3. So alpha beta is where the double bond was. So this is the alpha beta unsaturated ketone, or the Michael acceptor that was used, and the other half was the carbonyl. So that's how you would figure that out. So your different synthetic strategies. A Stork enamine synthesis will produce a 1,5 dicarbonyl compound. So the Stork enamine forms the enamine. We get an alpha beta unsaturated addition, and then we add water to that to get a 1,5 dicarbonyl. Aldehyde and clasins have 1,3 difunctional groups. The aldol will give you the 1,3 or the beta hydroxy ketone, or beta hydroxyaldehyde. If you heat that, then you get the alpha beta unsaturated carbonyl. The ester will give you a 1,3 or beta keto ester. So we learned about two methods to alkylate. You can alkylate using the alpha position, where the enolate attacks an alkyl halide, or you can use a Michael donor to attack the beta position of a Michael acceptor, or you can combine the reactions. If you take ethyl Cooper lithium, that will attack here, and the methyl group then will add here once you form that enolate. Okay, so on this first one we have ketone plus a secondary amine. We're going to form the enamine. There, which can then attack the methyl iodide. We also add acid to that, so I form a new group to CH3, which adds at this position right here, and then I'm going to reform the carbonyl plus the secondary amine. All right, if we want to perform a synthesis here, if I look at what is going on, if I do a retro here, this had to have come from this. So I need to add carbons. This one is a little bit trickier to see, admittedly. We have an ester here. We're going to do a malonic ester synthesis. So I have this, which probably came from here. So I'm going to use a base to deprotonate that alpha position. And in the process, I need to add, if this is the alpha carbon here, 1, 2, 3 carbons. So I've added my 3 carbons. If I want to get rid of this ester part, I'm going to add acid. I use acid and heat. The acid will hydrolyze that to the carboxylic acid. The heat will decarboxylate. So in this process, I'm going to subtract CO2. And then to do that reaction, I just need ethylene glycol plus catalytic acid.